now I'm going to hopefully deliver on some of those things that I said I'll get to later on. So this next section tries to go through this process that we kind of rushed through very quickly just now in a little bit more detail. And again, it's still a fairly high level, but hopefully we kind of start to move into a slightly more granular view on this. And this diagram here is showing a kind of quite a high level overview of this process of, going through these different steps to using a computer vision model. So you can see they have this kind of data preparation step, and often, depending on what you're trying to do, that will involve some kind of initial sampling. So in this case, this newspaper navigator data set is quite large. So I can't remember off the top of my head, but I think for the adverts, there's kind of, I guess hundreds of thousands, but maybe in the kind of high hundreds of thousands of images. And obviously what we're trying to do, even in that quite basic example, is to pick out some examples from that data, provide some labels that will pass to our model. And then that model can then hopefully predict on unseen examples and predict correctly what the label should be. And the reason this part is broken down into this kind of two stages. So I guess this label section in this particular example was quite straightforward. We had these kind of two categories of illustrated or not illustrated. But I think depending on what you're trying to do with computer vision, these kind of labels can be quite an important component, particularly if you are trying to do something that's perhaps more humanities orientated. So thinking carefully about what these labels should actually be often takes quite a lot of work, and is something that you kind of will have to come back to as well. And then this second kind of component of this labeling is this kind of annotation step. So this is the kind of step of actually doing some adding the labels to the images so the model has something to learn from. And then this is the kind of bit that we just looked at, really, is this kind of this loop where at kind of high level what we have is some training data, and in this case that was the images of adverts with their labels. We pass that into a model. So in this case we had this convolutional neural network model, and then we go through this kind of cycle, in this case 5 or kind of 6 times really. And basically what happens at this stage, in a very crude sense, is that the model makes some predictions based on the input data it gets, which in this case is the image, of what it thinks the label should be. It then checks to see if it was right or not. So it makes this prediction. And then depending on how right or wrong it was, it kind of updates itself. And we'll kind of talk about what that means. And tries to do a kind of better job next time round. And in this particular case, you can kind of already maybe get a sense that this is not a kind of necessarily a linear process. So we kind of see that this jumps around a little bit. So actually it goes down initially here and then goes back up. So depending on your model and data, this could be quite a bumpy ride. And it's also not a given, of course, that this will always improve. And then at kind of broad level, the kind of output of these predictions is also this metric. So we'll kind of discuss that a bit more, but you can see here that we have these kind of various different things reported to us. So this time, probably quite straightforward. We then have this accuracy score, which tells us, what % of the time the model is correctly predicting the right label. And then we have this thing called train loss and valid loss. And this is basically the way in which the model internally understands how right or wrong it's doing. And we won't cover this in proper detail in this workshop because it's quite a big topic. But I guess the thing I would kind of point out here is that these two scores have kind of slightly different purposes. So these training loss and valid loss, although they're telling the model how well it's doing, these scores are a little bit less human friendly to understand. So generally what we want to see is these scores kind of slowly going down. But it's not always the case that these scores directly map to this metric that we care about. So often when we're training a computer vision model or some other kind of machine learning model, we kind of choose some metric that we as a human, but also for our particular problem, care about. And this can, again, be quite an important consideration depending on the shape of your data, but also what it is that you want your model to do. This can have quite a big impact. And then I guess the final part, which can often be a huge part depending on what you're doing, is trying to interpret these metrics, but I guess also more broadly trying to understand how all of these different pieces fit together. Because I guess you probably will already have got a sense of this, but anything that you kind of do at these steps has a kind of quite a potential knock-on implication for these later parts. So how you kind of sample your data can have a big impact. So if you kind of sample in a way that doesn't represent the actual data you're going to show your model at prediction time, then you're going to get kind of interesting results or kind of bad results depending on how different it is and in what ways it's different. And again, with labels, depending on how those work, this can massively impact your metrics as well. So we'll kind of touch on some examples of that later on. So I'm going to skip over some of this kind of text heavy sections a little bit. So this is really talking about this kind of high level overview that I just went through. And what I'll do instead is kind of turn a little bit more to this deep learning part, which is basically this bit zoomed in, to kind of focus on that a little bit more directly. So in the previous diagram, this was quite broad, but as I kind of mentioned, this kind of loop process kind of goes through some initial steps before we get to that. And a lot of these things are kind of taken care of by this FastAI library, but it's still kind of important to be aware of how this is working underneath so we can kind of modify that if we need to. So the first thing that we'll often have to do is kind of prepare these batches of our training data. So I mentioned here that we don't have that many images, but often we'll still have too much data to kind of push all of it into a model at one time. So usually how these kind of deep learning models work is they kind of go through all of this data in batches. So the size of that batch will depend on various different things, but often it will be a number like 32 or 64, but it will vary depending on a variety of different things. And for each of those, basically, what the model needs is this image, and in this case, a label saying whether it's a illustrated ad or a non-illustrated ad. And these two obviously need to be put through together so that the model has both of these available when it checks its predictions. We then go through this kind of transformation step. So in our example above, that was basically when we resized all the images to be 224 pixels by 224. And then we put these into this kind of batch that I mentioned. And then for each of those, we kind of go through this process where, as I kind of mentioned, the model makes some predictions, it guesses, and then from those guesses, it calculates this loss score. So this is kind of how the model understands how well it's doing. And then from that, depending on this loss function or this loss score, so this is basically a number, the model updates its weight. So we'll kind of touch on that in a minute, but this is kind of the process by which the model gets better at making these predictions. And then we see this kind of metrics bit, which, although it's not kind of directly part of this training loop, so we could do all of this without having this metric, this is kind of how we can interpret more easily what's going on inside here. So that gives us a little bit more insight into how well this model is doing in a kind of more understandable way. So I'm going to skip over some of these bits because I think I've covered those a little bit. So I said I would get back to what this kind of ResNet 18 thing is. So when we kind of get to this process of creating a model, depending on what we're doing, this could be quite a involved step, or it could be quite straightforward. And in our case, we use this kind of type of deep learning model called a convolutional neural network. And this kind of diagram gives you, quite a crude version of what's going on inside one of these convolutional neural networks. So this is very crudely represented, but basically what this is trying to hopefully show is some intuition for how this works. So you can see here that we have this these three things that we call layers, and we have this input image, and then in this case we have these kind of two images that are supposed to represent an advert with some kind of illustration and an advert that's text only. And you can see these layers have these kind of pink areas. So basically when we say that we're trying to kind of learn something here, in this particular approach to machine learning, what these layers underneath represent, big matrices of numbers. So basically this is a bunch of numbers that the model has stored in these layers. And what we want to do is to have some way in which this input image, when it's passed through all of these different layers, is represented in a way that will be useful for predicting the correct label for that image. So in this case, the input image is text only. So what we want as the outcome of this image being pushed through all of these layers is some kind of representation of that image, which will be useful for saying, okay, that is an image, that an advert that's text only. So that's a very kind of crude overview, and we'll kind of dig into that a little bit more later on. But I guess the important points to kind of start to get your head around, if this is the first time you're seeing one of these, is that each of these layers is basically just a bunch of numbers. And we'll kind of get back to this, and probably this is really something that you might have an intuition for, but this input image for the model is also just a kind of bunch of numbers. So each of the pixel values is a number, and there's various different ways in which you can kind of represent images as a bunch of numbers, but underneath that's kind of how we represent the image on the computer. So essentially what's happening is this image represented as a bunch of numbers is passed through these different layers, which are also just a bunch of numbers, and then some prediction is made. And the kind of learning part is that each of these layers, depending on how you kind of set these things up, updates what these numbers are, with the goal of these numbers becoming useful for the particular task that you're trying to achieve. So in this case, that's predicting the text only or the visual only, but if it was something else, then these numbers would change in different ways. And this kind of loop process here is basically, again, in quite a crude way, how this process of the model takes this input data, makes some predictions, calculates how wrong it is, and then it does this kind of updating the weights. And that updating the weights refers to changing the numbers inside these layers. So what I would say here is that, I guess the art or the science, depending on your view of a lot of this, is in how you kind of combine these different layers and how you do this process of updating these numbers. And there's a lot of kind of things that you have to get right for this process to work. So that's, I guess, the tricky bit. But at a broad level, that's what we're trying to achieve when we're kind of creating this model and training it. This is a little kind of tool that you can play around with that should hopefully be useful for giving a little bit of an intuition about how these layers fit together. I think this is, it's kind of a nice thing to play around with. I'm not sure it will necessarily always make sense without some of that background, but I think it is quite a nice little thing to explore. So I think on a kind of, I guess on a more practical level, having kind of said that there's a lot of kind of considerations around how to piece these different components together. There's a kind of question in this kind of pipeline of going from data to model to predictions, of deciding what kind of model to use. And there's various different ways in which you could approach this. So one way would be to kind of define yourself some way in which you want a bunch of these different layers to be combined together. And that could be appropriate depending on what you're trying to do. But often you will want to use some existing model. So here there's an example where you can use a model that's already been trained on a task. So in this example, there's this kind of YOLO model, which is trained to predict bounding boxes. So these kind of images we saw on the newspapers, these kind of box around particular objects. So in this case, it's things like people, various animals. So I think there's probably an image somewhere. Yeah, so you have this like dog, and then the kind of thing that you have here that we don't have in our kind of classifier is not just that there is a dog, but there's also a box around that object. So that could be one kind of model that you potentially use. I guess one of the challenges, which I kind of mentioned briefly before, of using a model like this is that the data that you're using might be quite different to the data that this model was originally trained on. So you can probably see here, this is quite a different type of image to the images we had in our newspaper images. So that might cause problems. So that's something to kind of consider. As I mentioned, the other way is to kind of start with a model from scratch, where you kind of define how all of these different pieces fit together. But I think often in this kind of, I guess in this kind of setting where you're trying to achieve a particular task, what often has been found to work quite well is this technique known as transfer learning. And this is something that we'll kind of touch on in a little bit more detail in this kind of next section. But I'll maybe just pause there and see if there's any questions, because I realized that was quite quick maybe. Yeah, so I think it does depend, on I guess what task you're trying to do, and it can also, depend on your data. So in this particular example, this resize, we also kind of specified this squish method, and there's kind of different ways of doing this resize. So the other way you could do it is to kind of crop the image randomly. So quite often what the library will do is it will kind of randomly crop a particular section that will fit that size, with, I guess, the idea that each batch, hopefully part of what it's supposed to be learning to predict is featured in that crop. So the other kind of thing you can do would be to kind of, depending on what kind of data you're working with, if it's quite uniformly shaped, you could kind of define this, instead of being a square, as being a certain kind of ratio. So, example, if you're doing classification of movies, if they were all in the kind of same aspect ratio, then you might define it as, I don't know, 600 by 400 or something. But that's kind of slightly the weird thing sometimes intuitively about this this computer vision stuff, is that I think that I've lost my images, but is that the kind of way in which we see this doesn't always translate exactly to what the kind of model is seeing. And it's also quite difficult to always know exactly what it is that the model's picking out as important features. So I'll try and dig something out at the end, because there's some nice examples of that. But there's various different ways in which you can try and see which bit of an image the the model is kind of focusing on to make a particular prediction. So in this case, I would guess that it would be this bit that would be important for it to know that this was a kind of illustrated advert. And quite often those intuitions do sort of line up, but if it's a more kind of complicated image, so the examples that you often have as a kind of hello world of computer vision is classifying images of cats and dogs. And when you see what it is the model is kind of looking at to determine whether it's a cat or a dog, it's quite difficult for you as a human to make much sense of it. So I guess that's also potentially one of the downsides of these computer vision, these deep learning based methods, that it can be quite hard to interpret what exactly is going on to make the model make that prediction. And yeah, I think depending on what it is that you're trying to do, that can be a, oh well, or it can be like really bad. So I think it really depends on the kind of task that you're trying to do, how much I think it that can be a kind of negative. Yeah, so that you can define different aspect ratio. So I've done that quite often if there's something where, for example, like classifying pages of books, where the aspect ratio, it won't always be exactly the same, but it's usually not square, so it doesn't necessarily make sense to kind of make all of the images square. And there are kind of models that are able to cope with different sized inputs. So it's not always the case that you have to kind of do this resizing thing, but it's quite often for these kind of simpler models as a kind of necessary step. Okay, so yeah, this transfer learning bit is, I guess this bit I'm going to talk about a little bit more in the next part, so we'll come back to that. But I think this transfer learning part, what I think is really important, but it's also a little bit of a kind of soapbox, or I don't know, pet passion for me. So forgive me for banging on about this, but I think this is a really kind of interesting way of tackling these problems. And I think it's come up more and more in different uses of deep learning. And I think I mentioned when we did this fine-tune thing, you saw that there was this kind of downloading something thing that cropped up. And I said I'd come back to that. So basically what that was doing is downloading a model that was already trained to do another task. And then the other thing that I said I'd get back to was that there was this kind of two parts to this training process. So we had this kind of first go, and then we had this second go. And essentially what was going on there is we had this model that was trained on another task. And in the first epoch, so this kind of first zero, before it kind of goes through and does it 5 more times, we were only training the final layer of the model. So going back to our kind of very crude diagram, basically what we were doing is for the first pass through that model, we were just updating these weights, and all of these numbers were kind of frozen, so they couldn't change. And the kind of reason we do that is this idea of transfer learning is basically the idea that a model which has been trained on a previous task will often do better on a new task, even if that task, I guess, is fairly different in some ways. So there are limitations to this, but in the case of computer vision, quite often these models, that we kind of use as for transfer learning are trained on this thing called Imagenet. I don't know if I'm going to grab that. No. So yeah, I don't know if, I feel like quite a lot of people would have heard about Imagenet. I can never understand their website really, but essentially Imagenet is this kind of data set of images put into a lot of different categories. So I think it's 20,000 different labels, and these labels come from this kind of WordNet hierarchy, which is something from natural language processing. So that causes some kind of slightly weird things to crop up. So I think it's worth kind of mentioning that. And I think the authors of Imagenet have been working on this problem, but there's this kind of nice website here about some of these issues. And I guess it's not just that some of the labels are kind of weird or offensive, but sometimes the labels that appear in Imagenet kind of represent things that you wouldn't really think could be represented or don't appear visually. So one of the labels that I always remember is for philanthropist. So there's a kind of label and a bunch of images which have the label philanthropist, but I don't know how you can visually, just by looking at an image, say, okay, that's a philanthropist. So there's quite a few examples like that. I think just because of where the labels come from, which are slightly strange. But with those limitations in mind, often using these kind of pre-trained models that have previously had to kind of classify images on this Imagenet data set still works quite well. And this is kind of what we try and have a very crude experiment to try out here. And I guess I'll go on a little bit of a tangent here, and people might disagree with me on this, but I think the kind of field of computer vision and I guess deep learning has kind of, we probably would have had a lot of advances over the past 10 years. And that comes from a variety of different sources, but I think there's quite a lot of stuff in the field that is still kind of been empirically demonstrated to work well, but hasn't necessarily got a very kind of strong theoretical underpinning. So quite often people work out that something works well, and then later on someone fills in why that works well. So these things don't necessarily always start from first principles or kind of fundamentals. Often it's just that people see something works well in practice, and then at some point, hopefully someone works out a kind of a good explanation of why that is, or at least some kind of intuitions about that. And with that said, I think when you're then using these computer vision methods on a different domain to the one that is predominantly the one that kind of computer vision research works in, I think it's quite useful to be open to kind of experimenting and trying things out just to see whether they work. And this is a kind of very crude example of that. And I think this has previously blown up in my face, but we'll see if this is going to work. So in this case, we have the kind of exact same CNN learner that we had before, but we just changed this one flag to say that this pre-trained model is false. So previously, when we created this model, we used a model where all of these weights were based on being trained on Imagenet. So this model got very good at predicting all of the labels in Imagenet. So that includes a bunch of things like animals, plants, vehicles, all sorts of things. But But this time, what we do instead is we just say we want to kind of make those weights in all of those layers random. So we kind of start from scratch, as it were. And if we kind of train this model again, depending on how cooperative this is being, I'll either get the answer I want or I won't. But what you can see here is that compared to what we had up here, scroll all the way up, you can see that this model was a lot better in this kind of previous iteration of doing this compared to how it's doing this time round. So yeah, this kind of ends up fairly close to, well, I guess there's still quite a big gap. So it's not doing terrible, but you can see that at least in the number of epochs that we trained it for, this kind of pre-trained model weights seem to help. So yeah, we can kind of print that out. And so yeah, this is the kind of best score we got on our run up there. And this is the kind of best score we get here. And you'll see that some of these numbers here are kind of different to what is here. And I guess that it's worth pointing out that because of the way in which this model updates itself, I guess there's an element of luck and randomness to how well these scores do. So if you kind of train this model on the same data, you know, with all of the same parameters 5 times, you'll get 5 slightly different results. So that makes it a little bit annoying to write a notebook where you're trying to point to a particular number. But you can hopefully see that there is a kind of fairly significant difference between these two models. And yeah, as I've said here, this is obviously not a very convincing proof that transfer learning works, but I guess this next section tries to give some intuition for why that can work quite well. And I'll try and pull up a nice image of this later, but one of the things that people have found when kind of exploring this transfer learning process is when you have a model with all of these different layers, each of these tends to kind of learn slightly different features about the image. And in this case, we have kind of 3 layers, but in this in these models, usually we have quite a few more. And often what is kind of you see in these early layers, when you kind of look at what features they're picking out, is it will be quite basic features about an image, like does it have squares in it, lines, kind of particular shapes, basically. And as you kind of move through these layers and get closer to these final layers, you get kind of more complex and more domain specific features. So in this case, the kind of features that will be useful for predicting these adverts as being illustrated or not. And I guess the rough intuition then is that even though this model trained on Imagenet has seen kind of very different types of data, so Imagenet doesn't contain loads of historical newspapers, because a lot of the features that the model trained on Imagenet learns are kind of fundamental building blocks of images. Those will still be useful for other tasks, like predicting whether an image is illustrated or not. So knowing how to predict kind of lines, how to predict edges, how to predict circles, all of those features are likely to also be useful for predicting whether an advert is illustrated or not. And because this Imagenet model has been trained on kind of millions of examples of images, we basically, in kind of air quotes, get for free a model that's already knows quite a lot about the world. or knows quite a lot about how different images look. So often using that as a starting point works a lot better than kind of starting from scratch. And in particular, one of the advantages that we often get is that we kind of need less training data available, and we will kind of get a better performing model. And I guess the other kind of very nice thing about this is probably, yeah, I guess most people are aware broadly of the potential environmental impact training these models can have. So training a model on ImageNet, takes quite a lot of computational resource. But if we can use that kind of previous training to improve our results on a new task, then potentially it makes training on this kind of new task here much less kind of computationally expensive to do. So we've kind of seen that in other fields as well. So in natural language processing, there's also been a big move towards using transfer learning as a way of kind of training models to predict on text in a kind of, being able to do that with less training data for a kind of more domain specific example based on being trained on this kind of broader tasks before. So yeah, I've kind of in this section, there's some suggested things that I think we probably won't do now, but are things to kind of mess around with in these notebooks to kind of see how they impact on your results. And I guess, this really depends on how you enjoy learning. But for me, when I was kind of getting into this topic, I found it very useful to kind of just, go through notebooks and kind of change some of these parameters and see what the impact is, and then to try and dig into why that is having an impact. So to start with this kind of slightly crude messing around with things as a way of kind of developing some intuitions, I think can be quite useful, particularly I guess particularly in this field where I think there's still quite a lot of things that are kind of slightly artisanal in a way, and there's not necessarily a kind of defined correct way of doing this process of training a model that works well. So I think playing around with a lot of different examples can be quite useful. So that's the end of this first notebook.